Okay, um, in the last video, I show you that now I can do some load and save and end of front end of line. And now we will go to the MOL middle of line case, but everything is just similar, so I will just skip the intermediate procedures. So we'll just share the final result. So some of dielectric materials are intentionally neglected, and we are just looking at semiconductors and metals. Here you can see that this is the no, here you can see that the level corresponding to this cursor, and this is corresponding to the local interconnect. So one is one this one, the one at the center is corresponding to the local interconnect to the gate. So where can you find the gate? So for while just to eliminate something in no drain, drain. Mhm. So as you can see, uh, this is corresponding to no, this is central or local interconnect is directly connected to this gate. So now we have other one. Other ones are, you can find them here, and they are actually connected to this source and drain. So although they mean that LIG and LISD are existing in the same plane, as shown here, as shown here, but they have different connections. So some of them are connected to the source and drain, and some of them are connected to the gate. Okay, so this is a top view, and when you have a look at two-dimensional view, yes, now we can have this kind of shape. So sorry about the same colors. So currently I'm not controlling the color of each line. So red colors are assigned to both of substrate and yes, it's tungsten. But anyway, now you can understand these are connected to source and drain, and this one is the central one is connected to the gate. Well, up to now we have made a connection between this local interconnect level and internal contact such as source contact, drain contact, or um, a gate contact, but they are not still yet biased. Where can you find power lines such as ground or VDD? So that should be provided from back end of line, and this is just a local interconnect, and we have to introduce at least M1 level. So M1 level needs a little bit further elaboration because my simulation domain is set as just 300. However, we need more, so I will come back with even taller structure with M1 available. And another one is my structure just to contain the cell boundary. For example, In this case, this y directional size is corresponding to 10 times of a fin pitch, and this x directional size is corresponding to 3 times CPP. However, in this case, now we have to introduce BRs, but BRs are shared by this one single cell and neighboring cell. So I think that I have to a little bit enlarge the simulation domain to completely show you the BRs for this structure. So I will come back with a little bit enlarged system simulation domain. Well, my last comment is now I feel that for this interconnect part, actually, um, using this box seems to be quite inefficient because, you know, in the case of this front end of line part, actually we need even uh, finer grid because we wanted to have a better resolution for this kind of shape. However, once we go to this level, middle of line, then well, at least along z direction, the vertical direction, the size is quite large, and I guess that we don't have to spend too much effort on this uh, z directional part. But unfortunately, right now, the implementation of my uh, AngstromCraft code is just to support a uniform grid. So right now I don't have any solution to this inefficiency. Well, anyway, this is just the first trial of this code, so I will continuously improve this situation. Okay, thank you. And I think that now we are quite close to the end of this inverter example. And um, I now I have to prepare something beyond this Armstrong craft, although I have to continuously improving it. Uh, but now we move to another tool to get certain more valuable information out of it. Thank you and see you later.